Welcome to this coding walkthrough. Today, we'll explore problem number 241, different ways to add parentheses. This problem challenges us to determine all possible results from different ways of parenthesizing a mathematical expression. Let's dive in and break it down step by step. This problem asks us to take a string containing numbers and operators, and compute all possible results by grouping the numbers and operators in different ways using parentheses. The goal is to explore every possible parenthesization of the expression and calculate the results for each grouping. The operators we're working with are addition, subtraction, and multiplication. For example, if the input expression is 2-1-1, we need to consider all valid ways to group the terms, such as 2 to 1, -1 or 2-1 to 1. The output will be a list of integers, representing the results of all these computations. It's important to note that the answer can be returned in any order, as the problem does not require sorting. The input string will always be valid and will contain integers and operators, with no leading zeros in the numbers. To understand this better, let's look at an example. If the input expression is 2-1-1, we can evaluate it in two different ways. First, grouping the first two numbers together as 2 to 1, -1 gives us a result of 0. Alternatively, grouping the last two numbers together as 2-1 to 1 gives us a result of 2. Therefore, the output for this input is 0, 2. Now consider a more complex example, 2*3-4*5. Here, there are multiple ways to group the terms, and each grouping results in a different computation. The possible results for this expression are -34, -14, -10, -10, 10. These examples show how different parenthesis placements lead to different outcomes, and our task is to calculate and return all of these results. Breaking it down further, let's specifically examine the groupings for 2*3-4*5. One possible grouping is 2 times open parenthesis 3 minus open parenthesis 4 times 5 close parenthesis, which evaluates to -34. Another grouping, open parenthesis 2 times 3 close parenthesis minus open parenthesis 4 times 5 close parenthesis, results in -14. Similarly, grouping as, open parenthesis 2 times open parenthesis 3 minus 4 close parenthesis, *5, or, 2*, open parenthesis 3 minus 4 close parenthesis times 5 close parenthesis, both evaluate to -10. Finally, grouping as, 2 by 3, 4, *5, gives us 10. These groupings illustrate how parenthesization changes the order of operations and leads to different outcomes. As a simpler example, if the input expression is 2 plus 3, there's only one valid way to compute it, 2 plus 3 equals 5. In this case, the output would simply be 5, since there's no ambiguity in how to evaluate the expression. There are a few important constraints to keep in mind for this problem. First, the input string will only consist of integers and the operators plus, dash, and asterisk. The length of the string will be at least 1 and at most 20 characters. The integers are guaranteed to be non-negative, and there will be no leading zeros in the numbers. Additionally, the input string is always valid, so there's no need to handle invalid cases. For edge cases, if the input contains only a single number, like 3, the output should simply be a list containing that number, 3. For expressions with multiple operators, such as 2*3 plus 4-5, all possible parenthesization orders must be considered. Finally, since the input can be as long as 20 characters, it's crucial to ensure the solution is efficient enough to handle larger inputs without significant performance issues. To tackle this problem, one straightforward approach we can consider is the brute force method. This idea builds on the observation that we need to explore all possible ways to parenthesize the expression. The main intuition here is to split the expression at each operator, whether it's a plus, minus, or multiplication sign, and recursively solve the left and right parts. Once we have the results for both sides, we combine them using the operator in question. For instance, if the input is just a number, we can directly return it as a base case. While simple to implement, this approach has its drawbacks. The time complexity grows exponentially with the number of operators, leading to redundant computations for overlapping subproblems. This inefficiency makes the brute force method impractical for larger inputs but serves as a good foundation for more optimized approaches. The brute force method, while intuitive, suffers from repeated computations, especially when dealing with overlapping subproblems.
To address this, we can use memoization to optimize the solution.
The key idea here is to store the results of previously computed substrings in a dictionary or hash map. By using the substring as the key and its results as the value, we can reuse those results instead of recomputing them. For example, before calculating the result for a substring, we first check if it already exists in our dictionary. If it does, we simply reuse it, otherwise, we compute it and store the result for future use. This optimization significantly reduces redundant work while retaining the same logic of splitting the expression at operators and recursively solving smaller parts. The time complexity improves to cubic in the worst case, making this approach much faster for larger expressions.
Another way to solve this problem is through a dynamic programming approach that works bottom-up. Instead of relying on recursion, we iteratively compute results for smaller segments of the expression and build up to the full solution. To implement this, we use a table to store results for different segments of the string. Starting with shorter substrings, we calculate all possible results by iterating over potential splits within each segment. These smaller results are then combined to compute values for longer segments. While this approach is efficient and avoids recursion, it introduces challenges such as managing indices and handling string segmentation accurately. Despite its advantages, it may feel less natural to implement compared to recursion combined with memoization. The time complexity remains cubic, similar to the memoized approach, but the iterative nature makes it an alternative worth considering in certain cases. After evaluating the different approaches, we chose the optimized approach using memoization as our primary strategy. It strikes the right balance between simplicity and efficiency. Unlike the brute force method, it avoids unnecessary recomputation by leveraging a dictionary to store results for overlapping subproblems. At the same time, it is more intuitive and easier to implement than the bottom-up dynamic programming approach. One of the key insights here is recognizing the clear structure of overlapping subproblems in this task, where the same substring is often processed multiple times. The aha moment comes from realizing that memoization is a natural fit for this problem, as it directly addresses these inefficiencies. While the brute force approach is simpler and dynamic programming is efficient, memoization offers the best trade-off, making it well-suited for handling larger inputs effectively. Memoization stands out as the best choice because it combines the natural alignment of recursion with the efficiency of avoiding redundant computations. The recursive nature of this approach mirrors the structure of the problem itself, allowing us to decompose the expression in an intuitive way. By storing and reusing results for overlapping subproblems, it achieves significant performance gains without adding unnecessary complexity to the implementation. For most practical inputs, memoization provides a solution that is both easy to understand and efficient. Compared to the brute force method, it eliminates inefficiencies, and while dynamic programming offers similar performance, it requires a more intricate setup. Hence, this approach strikes the perfect balance, making it the most practical choice for solving this problem effectively. To understand this problem, we need to break down the task of evaluating all possible results from different ways of parenthesizing a mathematical expression. The key idea is that every operator in the expression provides a potential split point, creating smaller sub-expressions on the left and right. By exploring all possible groupings, we can compute every valid outcome. The brute force approach leverages recursion to achieve this. The base case is simple. If the input expression is just a number, there are no operators to split on, so we return that number as the only possible result. This forms the foundation of our recursive process. With the base case established, the recursive splitting begins. We iterate through each character in the expression, and when we encounter an operator, we treat it as a potential split point. The expression is divided into a left sub-expression, which includes everything before the operator, and a right sub-expression, which includes everything after it. Then, we recursively compute all possible results for both the left and right sub-expressions. Once we have these results, we combine them by applying the operator to every pair of results from the left and right. Each combined result is stored in a list, and after processing all operators in the expression, we return this list of results. To implement this, we define a recursive function called compute that takes an expression as input. The base case checks if the expression is a single number. If it is, we simply convert it to an integer and return it as a list containing that number.
For the recursive case, we initialize an empty list to store our results. We then loop through each character in the expression, and when we find an operator, we split the expression into left and right parts.
The function is called recursively for both sub-expressions to compute their results. Next, we combine the results using the operator and append the outcomes to our results list. Finally, the results list is returned.
To facilitate operator application, a helper function is defined to perform the arithmetic operations, taking two numbers and an operator as inputs and returning the computed value. The final output of the algorithm is obtained by calling the recursive function on the entire input expression. This function explores all possible ways to split and evaluate the expression, ultimately returning a list of all computed results. It's important to consider edge cases, such as when the input is a single number with no operators, or when there are no valid operators at all. Additionally, when dealing with large expressions containing multiple operators, the algorithm must handle the complexity of evaluating numerous recursive calls and combinations. This approach reveals several key insights. First, the problem naturally lends itself to recursive decomposition. Each operator splits the problem into two smaller, independent subproblems, which can be solved recursively. Second, the results from the left and right subexpressions must be combined pairwise for each operator, which necessitates the use of nested loops during the combination step. However, this process is computationally expensive because the number of recursive calls grows exponentially with the number of operators. For n operators, there are approximately 2n1 possible groupings to evaluate. To mitigate this, memoization can be used to store and reuse results of previously computed subexpressions, significantly reducing redundant calculations and improving efficiency. The algorithm primarily relies on two key data structures. First, lists are used to store possible results at each recursive step, allowing us to collect and return all computed outcomes. Second, dictionaries are employed for memoization to optimize the algorithm. Here, the keys are sub-expression strings, and the values are the lists of computed results for those sub-expressions. By caching these results, we avoid recomputing the same sub-expressions multiple times, which is crucial for handling larger inputs efficiently. Let's walk through an example with the input expression 2*3-4*5. The first operator we encounter is asterisk, so we split the expression into 2 on the left and 3*4*5 on the right. Solving the left part is straightforward, as it's a base case, resulting in 2. For the right side, we encounter the dash operator and split 3*4*5 into 3 and 4/5. Solving 3 is another base case, yielding 3. For 4/5, we split at the asterisk operator, resulting in 4 and 5, both of which are base cases with results 4 and 5. Combining these with the asterisk operator gives 20. Now, we combine the results from 3 and 20 using the dash operator, yielding -17. Finally, we combine the results from 2 and -17 using the asterisk operator, which gives the result -34. This is just one possible outcome, as the algorithm continues to explore other ways to split and group the expression. By systematically applying this process, we generate a comprehensive list of all possible results for the input expression. This example illustrates how the recursive decomposition, result combination, and memoization work together to solve the problem efficiently. This implementation solves the LeetCode problem number 241 different ways to add parentheses using a divide and conquer approach. The goal is to compute all possible results of an expression by evaluating it in different parenthesized ways. The function diffways to compute takes a string expression as input. First, it checks if the entire string is a number using isdigit. If so, it directly returns the number as a single element list since there are no operators to split the expression. The main logic involves iterating through each character in the expression. When encountering an operator, plus, dash, asterisk, the expression is split into two parts, left of the operator and right of the operator. The function then recursively computes all possible results for these two parts using the same method. The results from the left and right sub-expressions are combined using the current operator. For example, if the operator is plus, the results of the left and right parts are added. For dash, they are subtracted, and for asterisk, they are multiplied.
These computed values are appended to the results list. Finally, the results list, which contains all possible outcomes of evaluating the expression with different parenthesizations, is returned. This approach leverages recursion to explore all possible groupings of the expression efficiently. The complexity arises from the need to split and evaluate every operator, but it ensures that all valid combinations are considered. Edge cases, such as when the input is a single number, are handled by the base case check at the start of the function. Here, we begin the Java implementation for solving the problem of finding different ways to add parentheses. The method diffWaysToCompute takes a string expression as input. First, we handle the base case. If the entire expression is just a single number, we return it as a list containing that number. This is achieved using the helper method isNumeric to check if the input consists solely of digits. Next, we initialize a list called results to store all possible outcomes. Then, we iterate through each character in the expression. If a character is an operator like plus, dash, or asterisk, we split the expression into two parts, left and right, based on the position of the operator. These parts are then recursively passed into the diffWaysToCompute method to compute their respective results. This enables us to break the problem down into smaller subproblems, which we will later combine. After obtaining the results from the left and right parts of the expression, we combine them using the operator at the current position. For each value in the left results, we pair it with each value in the right results. Depending on whether the operator is plus, dash, or asterisk, we perform the corresponding operation and add the result to the results list. For example, if the operator is dash, we subtract the right value from the left value and store it. After processing all operators in the expression, we return the results list, which contains all possible computed outcomes. The helper method isNumeric ensures that we can identify numeric strings by checking each character to confirm it's a digit. This method is crucial for handling the base case. Overall, this implementation uses recursion to explore all possible ways to parenthesize the expression and compute the results efficiently. To start with example 1, the input expression is 211. The function first checks if this is a number using the isDigit method, which it isn't, so we move on to processing. An empty list called results is initialized to store intermediate computations. Next, we iterate over each character in the expression. At index 0, the character is 2, which is not an operator, so we move forward. At index 1, we encounter the dash operator. This prompts us to split the expression into two parts, 2 as the left subexpression and 1 to 1 as the right subexpression. These will be processed further in recursive calls. Now we dive into the recursive calls. For the left subexpression 2, the function detects that it's a number, so it returns a list containing just 2. For the right subexpression 1 to 1, the function processes it similarly by iterating over its characters. At index 0, the character is 1, which is not an operator. At index 1, we find the dash operator and split the expression into 1 and 1. Recursive calls for both 1 and 1 identify them as numbers, returning 1 and 1, respectively. These results are combined using the dash operator, giving us 0. Thus, the right recursive call returns 0. Finally, the results from the left and right calls, 2 and 0, are combined using the first dash operator, yielding 2, which is added to the results list. Continuing with the expression, we encounter the second dash operator at index 3. This splits the expression into 2 to 1 as the left subexpression and 1 as the right subexpression. Recursive calls are made for each part. For 2 to 1, a similar process is followed where the function identifies the dash operator, splits it into 2 and 1, and processes both through recursive calls. These calls return 2 and 1, which are combined with the dash operator to produce 1. For the right subexpression 1, the function directly returns 1 since it's a number. Combining these results using the second dash operator gives 1 minus 1 is equal to 0, which is added to the results list. At the end of this process, the final output for the expression 211 is 2, 0. In example 2, the input expression is 2 *3 4 5. Again, the function checks if it's a number, which it isn't, so we initialize an empty results list. Iterating over the characters, at index 0, the character is 2, not an operator.
At index 1, we find the asterisk operator.
The expression is split into 2 as the left sub-expression and 3-4*5 as the right sub-expression. These are then processed through recursive calls. For the left sub-expression 2, the function directly returns 2, as it's a number. For the right sub-expression 3-4*5, the function iterates over its characters. At index 0, the character is 3, not an operator. At index 1, we encounter the dash operator, which splits the expression into 3 and 4 by 5. Recursive calls 4-3 return 3, while 4-4 by 5, the function identifies the asterisk operator, splits it into 4 and 5, and processes each through recursive calls, returning 4 and 5. These are combined with asterisk to produce 20. Combining the results 4, 3 and 4 by 5 using dash gives 3 minus 20 is equal to minus 17, and 3 minus 25 is equal to minus 20, returning dash 17 minus 20. Finally, combining the left and right results 2 and dash 17 minus 20 using asterisk results in 2 times minus 17 is equal to minus 34, and 2 times minus 20 is equal to minus 40. These are added to the results list. Next, the function encounters the dash operator at index 3. The expression is split into 2 by 3 as the left subexpression and 4 by 5 as the right subexpression. Recursive calls 4 2 by 3 identify the asterisk operator, splitting it into 2 and 3, which are processed to return 2 and 3. These are combined using asterisk to give 6. Similarly, 4 4 by 5, recursive calls return 20. Combining the results 4 2 by 3 and 4 by 5 with the dash operator results in 6 minus 20 is equal to minus 14. This is added to the results list. The final output 4 2 asterisk 3 dash 4 asterisk 5 is 40, 46, minus 14. In example 3, the input expression is 3 plus 5. The function begins by checking if it's a number, which it isn't, so we initialize an empty results list. Iterating over the characters, at index 0, the character is 3, not an operator. At index 1, we find the plus operator. The expression is then split into 3 as the left subexpression and 5 as the right subexpression. Recursive calls for these subexpressions identify both as numbers, returning 3 and 5. The results from the left and right subexpressions, 3 and 5, are combined using the plus operator. This gives 3 plus 5 is equal to 8, which is added to the results list. The final output for 3 plus 5 is 8. To summarize, this solution recursively splits the expression at each operator and solves subexpressions independently. All possible parenthesizations are explored, and the results are combined systematically, making this an effective approach for solving such problems. To analyze the time complexity of this problem, we start by observing the recursive tree structure. At each step, the input expression is divided into two parts around an operator. For every operator, the function recursively computes all possible results for the left and right subexpressions. This process of recursive splitting is analogous to counting the number of ways to parenthesize an expression, which follows the growth of Catalan numbers. Mathematically, the nth Catalan number grows asymptotically as 4 to the power of n divided by the square root of n. This exponential growth in the number of recursive calls defines the dominant factor in our time complexity. Additionally, for each operator, the results from the left and right subexpressions are combined. If the left side yields k results and the right side yields m results, we have k times m combinations. This contributes further to the complexity, but it remains secondary to the exponential growth from the recursive structure itself, resulting in an overall time complexity of 4 to the power of n/sqrt, n. The time complexity is thus dominated by the Catalan number growth, giving us 4 to the power of n/sqrt, n. Now, shifting to space complexity, it also follows a similar pattern. The recursion tree depth is proportional to the number of operators in the expression, which is n. However, the total number of nodes in the recursion tree grows according to the Catalan number, leading to 4 to the power of n/sqrt, n nodes overall. Additionally, at each level of recursion, we store intermediate results in a results list. The storage for these results accumulates across all recursive calls, contributing significantly to the space complexity. Therefore, the overall space complexity is also 4 to the power of n/sqrt, n, driven by both the recursion stack and the storage of intermediate results.
When comparing this approach to a brute force method, the difference in efficiency becomes apparent.
A brute force approach would involve generating every possible parenthesization of the expression explicitly, evaluating each one, and collecting the results.
This results in factorial growth, which is computationally infeasible for large inputs. On the other hand, the recursive solution leverages dynamic programming principles, particularly if memoization is added, to avoid redundant computations. This optimization reduces the complexity to the Catalan number growth, which is significantly more efficient than factorial time. Looking at best, average, and worst-case scenarios, the best case occurs when the input expression contains no operators, such as a single number, where the function simply returns the number in O(1) time.
For expressions with n operators, both the average and worst cases follow the Catalan number growth, resulting in O(4 to the power of n/sqrt, n) complexity in these scenarios as well. To mathematically justify the time complexity, we can express the recursive calls using the recurrence relation t, n, equals the sum of t, I, times t, ni1, for all I from 0 to n1. This recurrence is identical to that of Catalan numbers, which grow asymptotically as 4 to the power of n divided by the square root of n. Consequently, the time complexity of the solution is O(4 to the power of n/sqrt, n). The space complexity follows the same reasoning, as the number of nodes in the recursion tree and the intermediate results stored grow in direct proportion to the Catalan number growth. This shared growth pattern solidifies both the time and space complexity at O(4 to the power of n/sqrt, n). When tackling problems like this, there are a few common mistakes that can trip you up. First, not handling edge cases properly is a frequent error. For example, if the input is an empty string or a single number, your program should handle these without unnecessary computations or errors. Skipping this can lead to runtime issues. Next, inefficient recomputations in recursive solutions can drastically slow down your code. Without memoization, the same subproblems might be solved repeatedly, leading to exponential time complexity. To address this, use a cache or memoization table to store results of previously solved subproblems. Lastly, defining the base case incorrectly in recursion is another pitfall. This can result in infinite recursion or incorrect results. For example, when splitting an expression, make sure the base case correctly identifies a single number instead of treating it like an operator. These foundational checks are essential for avoiding common runtime or logic errors. Now, let's focus on two more important mistakes and some valuable interview insights. Mismanaging operator precedence or associativity can lead to incorrect results. It's critical to evaluate expressions in the correct order, splitting the problem carefully at each operator. Additionally, not considering all possible parenthesizations is another common issue. Missing some combinations due to incomplete recursion logic can result in wrong answers. To avoid this, ensure that for every operator, you split the expression into all possible left and right subexpressions. From an interview perspective, this problem is a great example of divide and conquer combined with dynamic programming. Recognizing patterns such as overlapping subproblems and optimal substructure is key. It's also important to clearly explain your approach, including how you handle base cases and combine results. Visual aids like recursion trees can help you communicate your thought process. Finally, while brute force might work for small cases, most interviewers look for optimized solutions using memoization or dynamic programming. Be ready to discuss trade-offs in complexity and demonstrate your testing strategy for edge cases and large inputs. This problem is closely related to others you might encounter, such as LeetCode 95 and 96, which deal with unique binary search trees, or LeetCode 394, which involves decoding strings. Recognizing these connections can help you build transferable skills. Now, let's look at some alternative approaches and their trade-offs. A brute force recursion approach is straightforward and intuitive, especially for small inputs, but it's highly inefficient with a time complexity of O(2 to the power of n) for n operators. It simply doesn't scale well for larger inputs. A better option is to use memoization with recursion, which reduces redundant computations and improves time complexity to O(n*m), where n is the number of operators and m is the number of unique subexpressions. However, this still carries overhead from function calls and stack usage. For even larger inputs, a bottom-up dynamic programming approach can be more efficient, as it eliminates recursion overhead entirely. But keep in mind, implementing this can be more challenging and debugging might take extra effort. Finally, an alternative approach worth mentioning is iterative parsing with stacks. This method is particularly useful for problems that require immediate evaluation of expressions, such as decoding strings or evaluating reverse Polish notation. The advantage is that it handles single-pass evaluation effectively and avoids recursion. However, it's typically less intuitive for problems like this one, where you need to generate all possible results. Stacks are generally designed for sequential processing, so adapting them to handle recursive-like problems can be cumbersome. Understanding when to use this approach and its limitations will help you decide if it's the right tool for the problem at hand. Great work! In this session, we tackled problem number 241, reviewed the brute force approach, and discussed its strengths and limitations. Understanding recursion and divide and conquer is key to solving problems like this. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!